Sure, and I'm from the University of New South Wales. Today I'm going to be working through one of the previous class tests, test number 1, version 1A from 2010 semester 1. The very first question is asking us to sketch y equals x squared minus 2x minus 3. And then we need to sketch the absolute value of that function. So the first thing you need to notice is that x squared minus 2x minus 3 is a quadratic, so that's going to be a parabola when we sketch it. We do want to label the features of this parabola. They'll include some x and y intercepts as well as the vertex. So y equals x squared minus 2x minus 3. If we can factorize, that's a really good idea because that makes it easy to find the x-intercepts. So when we factorize this, we're looking for two numbers that multiply to give minus 3, that constant term, and add to give minus 2, that coefficient of x. So two numbers that multiply to minus 3 and add to minus 2 are minus 3 and plus 1. That tells us that this quadratic, x squared minus 2x minus 3, factorizes to x minus 3, x plus 1. You can check that works by expanding that out. Okay, so let's sketch our parabola. We're going to find some x and y intercepts. The reason we wanted to factorize is because now it's really easy to find the x-intercepts. To find x-intercepts, we always set y equal to 0 and we solve it. And if we want to solve x minus 3 times x plus 1 equal to 0, if two numbers multiply to give 0, well, one of them's got to be 0. So either x minus 3 is 0 or x plus 1 is 0. So we have two intercepts, x is 3 and x is minus 1. So the factorization helps us find the x-intercepts very easily. To find the y-intercept, we set x equal to 0. We can put it into either of these equations, but the top equation tells us that 0 minus 3, and so that's probably the easiest. The y-intercept is minus 3. So let's sketch what we have so far. We've got an x-intercept of minus 1 and an x-intercept of 3. We know it's a parabola. In fact, we know it's a concave up parabola because it's positive x squared, and it's got a y-intercept of minus 3. So if we sketch our parabola, it must pass through y equals minus 3 and these two x-intercepts there. Now the vertex of a parabola, that's this bottom point down here, its turning point. And that turning point will always occur halfway between the x-intercepts, if they have x-intercepts. So halfway between minus 1 and 3, well, that's just 1, but you could work that out by averaging the x-intercepts. So the vertex will be x equals, well, the average of minus 1 and 3, which we can do in our head. That's just x is 1. And if we substitute x equals 1 back into our original equation, we will find the y coordinate. So y will be 1 squared minus 2 times 1 minus 3, and that's minus 4. So our vertex is x is 1, y is minus 4, and I'll label that as a coordinate here, 1, minus 4. So we have a sketch of our parabola, y equals x squared minus 2x minus 3, showing x-intercepts, y-intercept, the y-intercept, and the vertex here. Now the second part of the question asks us to sketch the absolute value of that quadratic. So I might just rewrite it so we know what's on this side of the board. When we absolute value a number, it's got to be positive at the end of the day. So when we absolute value negative numbers, they have to end up positive. So we're absolute valuing the y value that we've just graphed here, right? So this parabola, we're absolute valuing this parabola. Here are all the y values that turned out to be negative. X squared minus 2x minus 3 is negative between minus 1 and 3 here. So if I had minus 3 and I absolute valued it, it would come up to plus 3. Minus 4 absolute values to plus 4. In fact, all these negative numbers here will absolute value to positive numbers. Positive numbers just absolute value and they stay exactly the same. So when we sketch graphs like this, what we're doing is we're reflecting any negative section of the graph about the x-axis to make it positive. So from -1 and to the left and from 3 to the right, these parts are going to stay the same, but this section in the middle we're going to reflect and it's going to become positive. The -3 intercept reflects to +3, that -4 reflects to +4. So now this vertex here is 1, 4. So just labeling some things here. So our first graph is just a graph of the parabola, and our second graph is the absolute value graph, where we reflected all the negative sections about the x-axis. Question 2 gives us a split function here. So for values of x less than or equal to 1, we use this rule 4x plus 1. For values greater than 1, we use the rule 7 minus 2x. And it's just asking us to evaluate the function at particular values of x. So f of 0 is asking us what is the value of our function when x is 0? Well, x is 0 is an x value less than or equal to 1. That means we're using this top rule here, 4x plus 1. So f of 0 is 4 lots of 0 plus 1, which is 1. F of 1, so the function value at x equals 1, well, 1 is less than or equal to 1, so we're still using the top rule here, certainly not bigger than 1, so we're still using the rule 4x plus 1, so 4 lots of 1 plus 1 is 5. F of 1 is 5. And in part 3, we want the function value at x equals 3. Well, 3 is bigger than 1, so we're using the second rule, 7 minus 2x. So f of 3 is 7 minus 2 lots of 3, and 7 minus 6, which is 1. So they're not asking you to sketch this function or anything, just to evaluate the function at particular values for x. Question 3 is asking us to solve an inequality. In a particular, an inequality with x in the denominator there on the bottom. The reason that these are particularly tricky is that you want the first step to just be to multiply by x minus 1 to get rid of the fraction. However, that's not a good idea as a first step because you don't know what x is. You don't know if x minus 1 is positive or whether it's negative, which means you don't know whether you have to flip the sign or not. You can solve it that way if you divide it into cases, but there are two other methods which are kind of less error prone, if you like, which are good ways to solve this problem. So we'll do two alternatives for question 3. The first alternative is going to be to graph y equals 1 on x minus 1 first. And that's out. So it's kind of a graphical method. We're going to graph this and then ask ourselves, when is that graph, when is the y value of that graph less than 3? Now I think I've copied the question wrong because it's not less than 3, it's less than 1/3. Okay, so let's graph this. It's a hyperbola and it's shifted right 1 unit. So that means this vertical asymptote is shifted right 1 unit. And our hyperbola is going to look like this. And we want to know, when is that hyperbola less than 1/3? Well, 1/3 is a positive y value, somewhere around here. Well, when is the y value of the hyperbola less than 1/3? Well, when it's underneath that line. So that's all these values here. Remember, that's 1. So in fact, all these values here are x less than 1. We can even read that off the graph. Plus all these values here. That's when it's underneath 1/3. So really, we want to work out what that point is, because x could be bigger than this x value here. Now, this is a point of intersection, so if we want to solve this, we just need to find that point of intersection. So for the point of intersection, we're just solving when 1 on x minus 3 is equal to a third. Because this isn't an inequality, we don't have to worry about whether to flip signs or not. We can just solve it cross multiplying, and then we obtain x equals 4. So this value here is actually 4. So our graph is less than or equal to a third for x bigger or equal to 4 on this side, or x strictly less than 1. It's strictly less than 1 because it can't be 1 because that's an asymptote there. So our final answer is that x is less than 1 or x is greater or equal to 4. We can write that using set notation. X is in the set. Well, it's a union because it's less than 1 or greater or equal to 4. Less than 1 means anywhere from minus infinity up to 1 but not including it. So we've got a round bracket here. Or, which is a union, 4, including 4, all the way to infinity with a round bracket for the infinity. So this is one way we can solve this inequality by graphing the hyperbola first, finding the point of intersection, and then reading off our graph what the actual answer is. Alternative 2 is a bit more algebraic. So for alternative 2, what we're going to do is we're going to multiply our first step. It's going to be to multiply both sides by the denominator squared. Here that's x minus 1 all squared. Something squared is always positive, so we don't have to worry that we have to flip signs, because we know we don't, because we multiply by a positive number. So if we multiply both sides by x minus 1 squared first, then we get x minus 1 here is less than or equal to a third x minus 1 all squared. And we're going to have to solve this. Now this is a quadratic inequality. This is x squareds here, x's here. We solve quadratic inequalities by bringing everything to one side and seeing whether the parabola, when the parabola is greater than 0 or less than 0. So we need to essentially bring it to one side and factorize it. You can bring this x minus 1 to this side and factorize it because x minus 1 is in common, although you might find that a little confusing. So I'm going to multiply by the 3 first, and I'm going to expand this and just refactorize it because I think you'll find that easier. So multiplying by 3 and expanding, we get this. And so 0 is less than or equal to x squared minus 5x plus a 4. And it's always nice to factorize it if you're going to solve an inequality. So this factorizes to x minus 4, x minus 1. They multiply to 4 and add to minus 5. So this is the factorization. Actually, I might write that as x minus 4, x minus 1 is greater or equal to 0. Remember the x's to be on the left. That says the same thing there. Okay, so when is x minus 4, x minus 1 greater or equal to 0? Well, when this parabola that goes through the x-intercepts 1 and 4 is greater or equal to 0. So this parabola is greater or equal to 0. It's above the axis. The y value is greater than 0 here and here. So that's x greater or equal to 4, and this is x less than or equal to 1. So we know x is less than or equal to 1, x is greater or equal to 4. However, remember the original inequality was 1 over x minus 1. X could never be 1 in the first place. So our solution, for our solution we have to remember x can't equal 1, and x is less than or equal to 1, or x is greater or equal to 4. And putting those together, we have x is less than 1 or x greater than 4, which is the same solution which we can write as a union of sets here. So there are two different approaches to solving this inequality with x in the denominator there. Question 4, we've got a surd here. A has the value the square root of 3 plus 1. We're asked to show that a squared equals 2a plus 2, first of all. So let's work out the left-hand side, that's a squared. Well, a is the square root of 3 plus 1. Sorry, a is the square root of 3 plus 1, so a squared is the square root of 3 plus 1 squared. When we expand this, we have to remember to square the first there, plus twice the square root of 3 times 1, plus 1 squared, which is 1. So that's the rule that x plus y all squared is x squared plus 2xy plus y squared. So just remember this 2xy in the middle here. So this gives us 4 plus 2 square root 3. So we can add the 3 and the 1. This is 2 root 3, but we can't add those together because I guess they're not like terms. Now the right hand side, well that's 2a plus 2. A is the square root of 3 plus 1. So we can simplify this. Let's expand here to get 2 root 3 plus 2 plus another 2. So again we get 2 plus 2 is 4 plus the 2 square root 3. So both of these equal to 4 plus 2 root 3. Therefore we know that a squared must equal 2a plus 2. Now we're asked to deduce that a to the n plus 2 is 2a to the n plus 1 plus 2a to the n. What we do here, the key is we multiply both sides of this result by a to the n. The reason you might recognise to do that is because here we have a to the n plus 2, and a squared times a to the n gives you a to the n plus 2. Bases are the same, and you're multiplying, you add the indices. So let's do that here. So we have a to the n times a squared must be equal to a to the n times 2a plus 2. Right? Because we know these are equal, so these must be equal. We've just done the same thing to both sides. Our index laws say that this is a to the n plus 2, and here we can expand. So this will be a to the n times 2a to the 1 plus, I guess I'll write a to the n times 2. So we're expanding. I just wrote 2 to the 1 there because we're about to use our index laws again. These bases are the same, and so I'm going to add those indices. So we have a to the n plus 2 is equal to, well that 2 is that 2, and a to the n times a to the 1 is a to the n plus 1. I'm going to add the indices, plus a to the n times 2 is just 2a to the n, which is exactly what we were asked to prove. So as required. So just expanding some surds here, and then realising that to get the final answer we have to multiply that identity we had by a to the n and use some index laws. Final question on this class test was involved a logarithm, so we needed to solve log y equals 2x for y in terms of x. So we need to make y the subject of this equation. There's two different ways you might think about this sort of question. The first way you might think about it I'm going to write this ln as log base e, just for the purpose of showing you what's going on. So ln y is log base e of y, and that equals to 2x. Now, this is a log way of writing an index. We can write this in index form, I guess using what I call the SOP rule, but however you want to remember it, by a definition of logarithms, this base to this must equal the y. Right? That's what a logarithm is. It's the power of this space that gives this answer here. So if we just rewrite this, we'll get e to the 2x is equal to y. That's writing it in index form. That's essentially solving it for y in terms of x. If you want to write y on the left, y equals 2 to the x here. Okay, so that's what I call the sock rule. You just draw this sock here, and that to the power of that equals that. That's the definition of the log. So that's one way you might think about this question. Another way you might think about this question, and you can write it as ln or you can write it as log base e, is logarithms and exponentials are inverse functions of each other. So if we do e to the power of both sides, right? Raise both sides to the power of e, we would get e to the log y is equal to e to the 2x. Right? We raise both sides of this equation to the power of e. Now, e to the power of log of y is just y, and that's because exponentials and logarithms, they're inverses of each other, they undo each other. So this is just y, and so y must equal 2 to the x there. So two different ways to think about this problem, but it's relatively simple once you understand what the definition of a logarithm is.